Something just woke up beneath the ice of Saturn's moon, and NASA is still trying to understand what this means. For 20 years, Cassini's cameras documented impossible chemistry happening in frozen oceans, light years away from Earth. But the real secrets? They were hiding in plain sight. Only now, with supercomputers and artificial intelligence piercing through layers of archived data nobody thought to examine closely enough, are scientists confronting a staggering truth. There's a world beneath that ice, a living world, and the evidence isn't theoretical anymore. It's sitting in laboratories, analyzed, confirmed, and absolutely real. What comes next will reshape everything we thought we understood about life itself. 21 million kilometers from Earth, beneath a frozen shell of ice stretching across thousands of miles, something has been moving, something we never expected to find. For nearly 2 decades, we told ourselves the story was simple. Saturn has rings, Saturn has moons. Cassini would observe, document, and return. We believed we understood the assignment. We were catastrophically wrong about what we were actually looking at. The spacecraft that was supposed to give us pretty pictures of a distant ringed planet instead stumbled into something far more consequential. It found evidence of an ocean, not a frozen, inert ocean of ice and silence. A living one, with chemistry, with heat, with the unmistakable signatures of something that should not exist in such a hostile place. When the data first arrived at NASA's Jet Propulsion Laboratory, scientists made a decision that would echo through the following decades. They marked certain images as inconclusive. They stored vast archives of raw data away. They published what they could explain, and they buried what they couldn't. That wasn't deception exactly. It was caution, scientific restraint, the careful approach of people who needed proof before making claims that would transform humanity's understanding of itself. But proof has a way of emerging when you're not watching carefully enough. Starting in October of 2025, something shifted. Advanced computational analysis, artificial intelligence trained to see patterns invisible to human eyes, and supercomputers pushing the boundaries of simulation began excavating through Cassini's archives with a hunger that previous generations of researchers simply didn't possess. What they found wasn't just data, it was a confessional, written in ice and chemistry. The images started telling a different story than the one originally told. The narrative wasn't changing. The narrative was being completed. From the south polar region of Enceladus, Saturn's small, seemingly insignificant moon, massive plumes of water ice, vapor, and something far more complex were erupting into space. Cassini had captured this phenomenon countless times. Geysers, simple, explainable geysers, water under pressure, perhaps heated by tidal friction, shooting upward and dispersing into Saturn's rings. That was the approved narrative. That was what made sense. That was what fit comfortably into established models of planetary geology. Except the more carefully researchers examined those plumes, the more the simple narrative began to crack. Inside those ice grains, particles no larger than specks of sand collected from less than 21 kilometers above Enceladus's surface, chemists discovered something that upended everything. Complex organic molecules, not simple carbon compounds, not basic building blocks, actual complex organic structures, the kind of chemistry you find in living systems, the kind of molecular sophistication that on Earth serves as the foundation for biochemistry itself. When the 2025 analyses were published, the language scientists used was deliberately cautious. They spoke of potential pathways to biochemical activity. They mentioned chains of reactions that could lead to life. They used words like significantly strengthens the case and provides new evidence. But the subtext was unmistakable. What they had found was alive or close enough that the distinction hardly mattered anymore. Think about what that actually means. Enceladus is a moon the size of a small continent. It orbits Saturn every 33 hours. Its surface temperature plunges to minus 190 degrees Celsius. The pressure at its poles would crush a human body instantly. By every measure we use to define habitability, Enceladus should be a graveyard of frozen silence. Yet beneath that suffocating ice shell lies an ocean. A global ocean with hydrothermal vents at its floor, with chemical energy flowing upward into darkness, with conditions that remarkably, impossibly resemble places on Earth where life thrives despite the absence of sunlight and the presence of crushing pressure. Extremophiles live in Earth's deep ocean vents near hydrothermal chimneys where temperatures soar and toxins flow freely. They derive energy not from the sun, but from chemistry itself, from the friction between hot mineral-rich water and cold, deep darkness. Everything Cassini found suggested that Enceladus possessed this same architecture. But there's something else. Something that transforms this from an interesting scientific discovery into something approaching a genuine revelation. The new data revealed that Enceladus releases heat not just from its south pole as previously believed, but from both poles simultaneously. This thermal distribution changes the timeline dramatically. A moon losing heat from both ends can sustain its internal ocean for billions of years. Billions. That means we're not looking at some temporary phenomenon, some brief window of geological activity. We're looking at a stable, enduring system. A system that could have maintained habitability for longer than Earth has had multicellular life. That's not just a moon, that's a potential biosphere. The implications began radiating outward almost immediately, though the mainstream scientific community moved with its characteristic deliberation. The European Space Agency began dusting off mission proposals that had been deemed too expensive, too risky, too speculative just years earlier. Suddenly, sending a spacecraft to orbit Enceladus, to land on its surface, to sample those plumes directly, seemed not like science fiction, but like an obvious necessity. The psychological pivot was subtle but profound. We went from asking, could there be life on Enceladus, to asking, how quickly can we get samples from its oceans? That distinction matters. It represents a fundamental shift in how the scientific community views an entire world. What makes this moment genuinely staggering is understanding the scale of what had been sitting in NASA's databases all along. Cassini made 294 close flybys of Enceladus, 294 opportunities to study this distant moon intimately. 294 windows into a world that was trying to tell us something if we had only known how to listen. The spacecraft's cosmic dust analyzer, an instrument so sensitive it could detect individual molecules in the ejected plumes, gathered data that should have transformed everything immediately. Yet bureaucracy, caution, and the simple fact that processing terabytes of data from the outer solar system wasn't the priority, it might have been meant that we were analyzing pieces of this cosmic puzzle decades after the information arrived. And now the analysis was accelerating. Researchers identified not only molecules that had been detected before, glycine, organic compounds, hydrogen, and methane, but entirely new organics that had never been found in Enceladus data before. Some of these molecules don't appear in lifeless planetary chemistry. They emerge from living processes. They are signatures. When you find them, you're seeing the fingerprints of biochemistry itself. On Earth, these molecular signatures would point directly to life. In the cold plumes of a distant moon, they point to a question humanity has been asking since consciousness emerged from mud and matter. Are we alone? The data refused to be ignored any longer. By November 2025, as supercomputer simulations refined models of how those plumes actually behaved, showing that the geysers were losing 20 to 40% less mass than originally estimated, which meant the subsurface ocean was far less volatile and therefore more stable, the scientific consensus had shifted into something approaching mainstream acknowledgement. Enceladus was not a curiosity. It was a target, a world that demanded to be explored thoroughly, carefully, and soon. The consensus shifted from, this might be interesting, to, we need to know what's living there. And here's what makes this truly consequential. Cassini is dead. The mission ended in 2017, crashing deliberately into Saturn's atmosphere to avoid any possibility of contaminating Enceladus with Earth microbes. We sent our last probe to this distant realm nearly a decade ago, and it could not have provided us with more important information had it been designed specifically to answer the existence question of extraterrestrial life. The universe, it turned out, had already done the hard work. It had placed a habitable world within reach of our technology. Cassini simply documented the arrival of that revelation. We just took far too long recognizing what was being shown to us. Consider the timeline of this unfolding discovery. In 2005, Cassini first detected the plumes. Scientists noted them with interest. Over the following years, additional data accumulated. In 2014, the full picture of Enceladus's global subsurface ocean was confirmed. In 2017, evidence of hydrothermal activity emerged. In 2018, organic molecules were first identified. Each discovery was announced separately, each celebrated modestly within the scientific community, each quickly absorbed into the general background noise of space news. But by 2025, when the complete picture suddenly came into focus, when advanced AI began excavating patterns from archived data, when supercomputers started simulating subsurface conditions with unprecedented precision, when new organic molecules never before detected were identified in ice samples, the collective understanding underwent a phase transition. This wasn't incremental discovery anymore. This was confirmation of something that changed categories entirely. What most people are not seeing is that this isn't just about Enceladus. It's about the implications that ripple outward from Enceladus toward every other world we've been studying, Jupiter's moon. Europa possesses a similar subsurface ocean beneath its icy crust. NASA's Europa Clipper spacecraft launched in October 2024 and following an orbital strategy directly inspired. by Cassini's methods, is currently making its approach toward Jupiter's system. The questions being asked about Enceladus are the exact same questions that will be asked about Europa. Does that moon harbor complex organics? Does it release heat from its poles? Could it sustain life? The Europa Clipper will spend years studying that distant ice moon using lessons learned from Enceladus. The sequence of discovery is accelerating. The implications are compounding. There's Saturn's moon Titan as well, with its nitrogen-rich atmosphere and surface lakes of liquid methane. A completely different kind of world, with chemistry unlike anything we find on Earth, yet potentially hospitable to forms of life we haven't even conceptualized. There's the possibility of subsurface oceans on moons around Uranus and Neptune, worlds that have barely been visited by human spacecraft. There's the growing realization that the outer solar system is far more active, far more chemically diverse, and far more potentially habitable than models from even 5 years ago would have suggested. Cassini opened a window. The light streaming through that window is only now being fully perceived. The real story is that we've been living in ignorance of our own cosmic neighborhood. We built sophisticated instruments, sent them to the edge of our planetary system, and gave them instructions to observe and document. The data came back. We processed some of it. We filed most of it away. We moved on to other projects, other priorities, other questions. It took artificial intelligence, supercomputers, and a gradual shift in scientific perspective to recognize that we had already found something extraordinary. We just hadn't assembled all the puzzle pieces into a coherent image until now. And this is where everything changes. The discovery of complex organics in Enceladus's plumes isn't a theoretical milestone, it's a practical one. These are actual molecules we can analyze and understand. The implications are testable. Future missions can be designed to answer them. The European Space Agency's proposed Enceladus orbiter mission would do exactly that. Collect samples, analyze their composition in unprecedented detail, search for amino acids and other molecules that point unambiguously toward biochemistry. If that mission launches, if those samples are analyzed, if complex organics are confirmed in even greater detail, the discussion will shift again, not toward could there be life on Enceladus, but toward what kind of life exists on Enceladus. The stakes have become profoundly personal in a way that abstract discussions of extraterrestrial life have never been before. We're not talking about discovering microbes in metaphorical puddles on alien planets. We're talking about a world that's been actively broadcasting signals, chemical signals, thermal signatures, geysers that have been visible to our telescopes for years, announcing its existence and its potential habitability. And we almost missed it entirely. We had the data. We had the technology to analyze it. We simply lacked the framework to interpret what it meant. What this really signals is a transformation in how humanity understands its place in the cosmos. For centuries, we inhabited a universe that seemed fundamentally different from the one we lived in. Space was cold, empty, inhospitable. Life was assumed to be a unique accident, something so contingent on specific conditions that finding it elsewhere seemed vanishingly improbable. But every new discovery from Cassini, every piece of data returned from the outer solar system, every photograph of distant worlds revised that narrative in a single direction. Habitability is not rare. Extreme environment S are not necessarily lifeless. The chemistry that gives rise to life is not unique to Earth. It emerges predictably wherever the right conditions exist, and those conditions exist more commonly than we ever believed. The data doesn't scream this conclusion. It whispers it methodically, patiently through countless papers and presentations and images analyzed by teams of researchers working in careful increments. But the accumulation is undeniable, and Enceladus sits at the center of this transformation. A small ice moon proving that the universe is far more generous with the gift of habitability than our philosophers and our scientists once imagined. Read that again. We discovered evidence of a potentially habitable world orbiting Saturn. We spent decades analyzing that evidence. We finally, in 2025, recognized what we'd been looking at all along, and we're only now beginning to consider seriously what our next steps should be. The significance of this moment is not that it proves extraterrestrial life definitively. It's that it transforms that question from something abstract into something concrete. We can now ask not, does life exist elsewhere? But when will we find it? The shift from possibility to probability represents a fundamental rupture with the past. There are still enormous questions that remain unanswered. No one has sampled the actual subsurface ocean of Enceladus. No one has isolated living organisms. No one has proven that the complex organics discovered in the plumes actually constitute life, rather than simply serving as precursors to life. The caution of the scientific community remains justified. But caution is different from dismissal, and the fact that serious, funded missions are being proposed to return to Enceladus represents a shift in how humanity is taking these possibilities seriously. The real revelation of Cassini's secret images isn't what they show. It's what they suggest we're still in the process of discovering. There are worlds out there, in our own solar system, in the shadows of distant stars, in the far reaches of the cosmos, that are different from Earth, but not fundamentally less habitable. There is chemistry happening on distant moons that mirrors the chemistry of life itself. There are oceans under ice that maintain stable conditions for billions of years, and we are only beginning to ask the right questions about what those conditions might harbor. We sent a spacecraft to Saturn expecting to observe. Instead, we received an invitation. The only question that remains is whether we accept it, whether we commit the resources and the will to return to these distant worlds and answer the questions that Cassini's data has placed squarely in front of us. The images aren't secret anymore. They're being analyzed in laboratories around the world. They're being discussed in scientific journals. They're being incorporated into mission proposals and funding applications. But the real secret, the one Cassini discovered and transmitted back across the void, is that the universe is not as empty as we believed. That life, in whatever form it takes, is not a rare anomaly struggling to persist in an inhospitable cosmos. That habitability is an emerging rule rather than an exception. And that right now, in the closing decades of the 21st century, we stand at the threshold of confirming this truth through direct observation and sample collection. What comes next depends not on what Cassini found, but on whether we have the courage to follow where those discoveries lead. The data is waiting. The questions are posed. The framework for understanding is in place. And somewhere beneath the ice of a distant moon, orbiting a ring giant that hangs in the darkness of space, the answer to humanity's oldest question may already be alive, waiting patiently for us to finally arrive.